All right, we're going to finish talking about current electricity. Today we're talking about how energy is transferred in electric circuits. So when the charge leaves the voltage source, it'll have a certain amount of electric potential energy. As that charge flows through the circuit and encounters the device that we were talking about, there's at least one device in the circuit that has that resistance. That device, again, transforms that energy into some other form of energy, light, heat, sound, whatever, and uses up the electric potential energy that that charge has. So as the charge flows back around to the voltage source, it gets back to the voltage source with zero electric potential energy. Then the voltage source does work on it again to increase its electric potential energy and send it back out through the circuit. Electric power, again, is the electrical energy per unit of time that is converted into another form of energy. So again, power, we used to define that as work divided by time. The other definition of it was the amount of energy transferred per unit of time. So when we talk about electrical power, we're talking about electrical energy transferred per unit of time. So power, again, is equal to the voltage times the current. Power can also be found by taking the current squared times the resistance. If we think about that, Ohm's law says that resistance is equal to voltage divided by current. So voltage, to rearrange the equation, voltage is equal to current times resistance. If we substitute this into the equation here for current, or excuse me, for voltage, we'd have current times resistance times current, or current squared times resistance. Not sure why I have this delta here, but since voltage can equal current times resistance, like we just showed, we can also make some other equations for power. We just showed how to get this one. If we take this equation and rearrange it for current, Ohm's law equation, current would equal voltage divided by resistance. If we substitute that into the equation for power, we have P is equal to V over R squared times R. So P equals V squared R over R squared. And that cancels out to P equals V squared over R. So that's how we get to this equation. And then we saw yesterday that energy is equal to power times time. So we can substitute any of our equations for power into this energy equation. And one of the things, for example, that we could get is energy is equal to I squared R times time. When electrical power companies transmit power over long distances. This is what they're concerned with, the current and the resistance. The power lines that they transfer energy through, electrical potential energy through, all have a natural amount of resistance. And so that's why they transfer the energy at high voltage, so that it keeps the amount of energy that they lose to that natural resistance to a minimum. So this is what I was just talking about. All those wires have a certain amount of resistance. For example, wires used to carry energy to homes have a resistance of about 0.2 ohms per kilometer. So since energy can be lost due to that resistance in the wires, they minimize that loss by increasing the voltage, which keeps the current low. Take a quick look at an example problem. A heater has a resistance of about 10 ohms. It operates on a 120 volt circuit. So the voltage is 120 volts. Letter A wants to know what is the current. So for that, we just need the Ohm's law equation. R equals V over I. So I equals V over R. Take the 120 volts divided by the 10 ohms, and we would have 12 amps of current. Letter B wants to know what thermal energy is supplied by the heater in 10 seconds. So they give us a time of 10 seconds. They want to know how much energy gets transferred. Since we were given the resistance and the voltage, we know that energy is equal to power times time. We would use the equation for power, that is V squared over R, since that's what we were given to work with. So we take 120 squared divided by 10 times 10 seconds. And that comes out to 14,400. Joules of energy. And lastly, the electric energy companies provide us electrical energy. They don't provide us power, they provide us electrical energy. They measure that amount of energy in kilowatt hours, because watts and seconds are very small units. So a kilowatt hour is equal to 1,000 watts, that's what a kilowatt is, delivered for 3,600 seconds. So that's equal to 3.6 million joules of energy. Take a quick look at how that works. So for example, a modern color television draws 2 amps of current when operated on 120 volts. So we have current of 2 amps. Voltage of 120 volts. Letter A wants to know how much power the set uses. For that, we can just use power is equal to voltage times current. So 120 volts times 2 amps. That's 240 watts of power. And it wants to know if the set is operated for an average of 7 hours per day, what energy in kilowatt hours does it consume in 1 month or 30 days? So we have 7 hours per day. And we're going to operate it for 30 days. So we want the power in the energy used in kilowatt hours. Energy again is power times time. So to get it in kilowatt hours, we simply have to put the power in kilowatts. If we have 240 watts, there's 1,000 watts in a kilowatt, so that would be 0.240 kilowatts. And then for the time, if we want kilowatt hours, the time needs to be in hours. So 7 hours per day for 30 days would be 210 hours. So put the power in kilowatts, the time in hours, multiply them together, and we would have 50.4 kilowatt hours. And the last thing it wants to know, at 11 cents per kilowatt hour, what is the cost of operating this television for 1 month? So we have a rate of 11 cents per kilowatt hour. Cost is equal to the energy used times the rate. So we use 50.4 kilowatt hours in 1 month at a rate of 11 cents per kilowatt hour. So to watch a television for 7 hours a day for 1 month at 11 cents per kilowatt hour would cost us $5.54. All right, that's the end of what we're talking about with current electricity. Hopefully you should be able to handle this worksheet now. Thanks.